Thank you very much, Gwen. So I like to talk about building real-time data products. This comes from our experience at LinkedIn. At LinkedIn, we have a lot of data, and we use that data to build a lot of products. And Apache Samza is an open source project that we developed to help us build those products. So my name is Martin. I was, until recently at LinkedIn, I actually left a short time ago to work on a book, so I'm currently full-time taking a sabbatical to write this book for O'Reilly called Designing Data-Intensive Applications. This book it's trying to be a kind of really broad overview of the big ideas behind all sorts of different data systems of databases, batch processing, stream processing, caching, indexing, and all of the big ideas which connect all of those together. You can find an early release of that book online at dataintensive.net, or I'll actually be handing out free copies at 3:15 p.m. tomorrow afternoon over in the expo hall at the O'Reilly authors booth, if you're interested. But anyway, I'll be talking about Samza in this talk, which you can find on the Apache incubator. Samza is a distributed stream processing framework. So let me just give a bit of background. If you've seen things like Storm or Spark Streaming, they're in a kind of similar sort of environment. The idea is you have some kind of stream of events which you want to process as they come in, and you want to distribute that processing, that computation across multiple machines, hence distributed. The streams we work with, you can think of just as sequences of messages, which are in some order, and there's some process which produces those messages. So, for example, that could be a web server process, which every time somebody loads a page, that sends a message to a message broker, to the stream. And then anyone who's interested in learning about the fact that somebody just loaded a page can consume the stream and can do whatever they want with it. So, by analogy, if you're using a batch processing framework, say MapReduce, you would have typically some input data set located on the Hadoop file system at some path. You might have several inputs to your job. You then run this job, which reads that input, which consumes that input, and produces output to some other location. And that'll typically be some other path on HDFS. And this job will be something that you run periodically. So say, for example, once a day. Whoop, hey, my thing is going nuts. Stop. Wow. Sorry, that was my clicker going nuts. Let me try that again. No? Okay, never mind. Okay, here we go. So what Samza tries to do is it fits a very similar kind of conceptual model where, again, you have some inputs of stuff that you want to process and you're producing some outputs. But rather than this being a batch process, which you run, say, once a day or once an hour, this is a process which runs continuously and processes messages just as they come in with fairly low latency, usually. In our case, the best way of using Samza is together with Kafka as a message broker. You can connect it to other kind of message brokers which you want, but we rely quite a lot on Kafka's semantics, which makes a lot of the way that Samza operates very well. And we really wanted to emulate this kind of input to output model in Samza like you have in MapReduce, where you're taking some input data sets, transforming them, processing them in some way, and producing some outputs. And then you can chain these things together, which allows these kind of data pipelines to be built, which can potentially span multiple teams within a large organization. So I should perhaps clarify the relationship between Kafka and Samza. These are both open source projects, Apache projects, which have come out of LinkedIn. The two teams which developed these two sit directly next to each other, and they're very closely connected. Kafka is a message broker, so it takes care of, if you have a message that needs to go from A to B, it takes care of that. It does that in a way which is durable. It actually writes everything to disk, and it's still fast, nevertheless, despite writing everything to disk. It takes care of fault tolerance, so you can lose machines and not lose any data. It's optimized for very high throughput. It provides a a stream of ordered messages which one person can publish, and then any number of different processes can consume that stream. So that's what Kafka is. Samza is the processing counterpart to that. So if you have the stream of messages, you want to do things like filter it, you want to aggregate it, you want to join streams together. And that's the kind of framework that Samza provides. It's really at an analogous level of abstraction to MapReduce. So it's a fairly low level of abstraction, but it still handles fault-tolerant things for you. It also handles deployment tooling for you, which is actually quite nice. So it can be deployed in different ways, but the default way of deploying it is through Yarn. So it can actually live on a Hadoop 2 cluster alongside other Yarn applications, alongside Tez or MapReduce or whatever it is you want to run. Samza is well behaved in that way. And this is actually a very nice way for us to reuse all of the existing excellent work which is going into frameworks like Yarn as a way to deploy your jobs. Anyway, so that's as much as I want to introduce about Samza. I think it'll be helpful to talk about some example use cases of how Samza is used at LinkedIn, because I think that helps illustrate some of the interesting features that it has and some of the design ideas that went into it, and also some of the ways that distinguishes it from other stream processing frameworks. I'm going to talk through two examples in detail. And the first example I want to talk about is, assume you have a stream of tracking events and you want to enrich those. I'll explain in a moment what I mean with that. So say your tracking event, for example, is what we call page view event. So that's this example of you are a website or a mobile app or something of that sort, and every time a user does something, you want to log the fact that the user does something. And the way in which you log that fact typically looks something like this. So using a kind of JSON-like notation here, you'll have an event whose type is page view event. Typically, it'll have a timestamp associated with it, which is when did this thing occur. And in the case of somebody loading a page, well, that somebody in this case is a logged-in user. So we have their user ID, in this case 1234. We have some kind of session ID, which might be a random number from their cookie, which tells us if there's a sequence of page views, that all of these page views belong together to one user session. We have a page key, which just identifies what kind of page, what kind of URL was actually loaded. So in this case, for example, it might be looking at somebody's LinkedIn profile. And you might also be interested in other metadata, like, for example, how did the user actually get to that page in the first place? You know, maybe they clicked a link in an email, which then caused them to open the browser and load that page. That's really useful information for analytics purposes to know. So all of this can be stuffed together in an event and be published to Kafka. So this is a page view event. And now, once you have this stream of the page views from all of the users on the site, you can do lots and lots of really interesting things with it. So one of the things you can do, for example, is you can track every time somebody looked at a profile, and you can tell the owner of that profile who viewed their profile. And you probably know this feature from LinkedIn. It looks something like this. It was actually recently redesigned, so it looks quite snazzy now. It's kind of like a Google Analytics thing for your LinkedIn profile almost. And you can see there's a graph of, for each weekly bucket, how many profile views you had, and it gives you some a sample of the actual users who viewed your profile. So this is one of the things you can implement if you have this kind of stream. Another thing that you could implement is a people who viewed X also viewed Y. This is a collaborative filtering application. It looks something like this. So say, if you look at my LinkedIn profile, you'll see on the side next to it in the sidebar a widget which looks like this. People who viewed Martin also viewed Rahul and Sam and Jay and Rashmi and so on. So the way this was created was by taking all of these profile views and seeing what are the co-occurrences between different profile views, one viewer looking at several different profiles. This is interesting stuff you can do. There's lots more you can do. You know, you can train relevance models in order to then improve the quality of a newsfeed, for example. You can monitor the speed of the site, the performance that users are actually seeing, and see if there are any performance issues on some internet provider somewhere in the world. You can use this for reporting, for telling summary statistics to the executives or to Wall Street. You can do this to analyze the results of A/B tests. to see whether users in the A bucket behaved any differently from users in the B bucket. So once you have this stream of events, there's a whole bunch of broad things that you can do with it. And of all of these, I just want to focus on one of them for now, which is who viewed your profile. So, as I said, it looks something like this. And a few things to notice about this. So imagine what you would do if you wanted to implement this kind of feature here. So you would obviously consume the stream of all of the page view events, which tells you what profile views happened. And then here, okay, we've got a count per week. So you need some kind of bucketing over weekly time periods and then aggregate in order to count the number of events in each time period and group that by the profile that was viewed. That makes sense. If we zoom in here, you can see a few more details. So for example, this thing is actually telling us that some number of viewers of my profile are people who work at LinkedIn. That's, I guess, not too surprising, given that I also worked at LinkedIn. It also tells me something about the job title of the people who viewed my profile. That's kind of interesting, because so this system here knows that 70 people whose job title is software developer viewed my profile. But if you look at what this page view event looked like, there's nothing in here that tells me what is the job title of the person who viewed the profile. That's a separate data set. So we know, of course, the job title of the person who viewed the profile. That's in a separate database. It's not in this event. So that's what I mean with enriching this data. We need to take these page view events, which only contain the ID of the user who viewed the page, but not any additional information like their profile information. And we need to augment that event with profile information. So what we need to do is when we have this augmented information, then this enriched data, then we can index it, then we can figure out, like, is a certain job title dominant amongst the viewers of this profile, and then you can group it by that job title, and then you can aggregate it and count it, and that gives you this statistic. So the first step you have to do there is actually take the stream of events and enrich them accordingly. So let's talk about implementing that. Well, this can be a stream process. We want it to be a stream process, not like something in a MapReduce job, because we want your who viewed my profile to be quite up to date. You know, we don't want to wait a day from someone viewing a profile before the stats show up. We want it to show up quickly. So we need to process this data in real time. So we need a stream processing job. That stream processing job will consume the stream of page view events, which will contain the ID of the person who viewed the profile. It will do something, and it will emit another stream of page views augmented with the profile of the viewer. And then once you have that, you can then further index that stream that you've created. Now, how do you do that? Well, of course, you have to ask some database. So you have to have some database of profiles on the side where if you get in, here's an event by user 1234, I have to ask that database, hey, can you give me the profile for user 1234, which includes the job title and other information, get that data back from the database, pack it into the event, and emit that combined event back out to a new stream. So that seems reasonable, but the problem is that is terribly slow. Because if you're here talking to some remote database that's, you know, on the other side of a network connection, even within a data center, you'll probably have like a millisecond or so latency. But, you know, this system should be able to handle hundreds of thousands, if not millions, of messages per second. If you're talking over the network for every single message, that is just not going to work. It's very similar to what Taylor was talking about in the last talk with Storm. So, well, the obvious solution to something being slow is obviously we add a cache. Everyone loves caches, so we'll add a cache there, and now, unfortunately, we just have more problems. So if you add this cache now, well, if you make the expiration of the cache too short, then your hit rate is too low and you haven't really gained anything at all. If you make the expiration of the cache too long, then you've got a whole lot of stale data in your cache, and when you augment the events, you're joining it against some old profile. And there's actually, even in addition to that, there's a more insidious problem. The problem is described in this graph here. Can you see that? This is an actual production graph from LinkedIn systems. And it shows the number of queries per second to a database cluster. And during the day, like at normal busy time of day, that's doing like 6,500 or 7,000 queries per second, and that's fine. It can handle that quite happily. And so then you look, and then at some point, suddenly the query throughput drops. And it stays near to 0 for about half an hour. And then it spikes massively to like 24,000 queries per second. So it spikes up to like 3 or 4 times the normal throughput, and then it continues as normal. What happened here? Well, the answer was this was a stream processing job, which was consuming a high throughput topic, something like page view event. And that job got shut down, maybe for maintenance, deploy a new version, maybe something went wrong in the system. Normally, shutting a job down for half an hour is not really a big deal. So it was down for half an hour, then it was brought up again. Now, when it came back up, it had to process the backlog of messages which the job missed while it was down. Now, this is a stream processing framework. It has good performance, so it can crunch through that backlog of messages in no time at all. So it goes really quickly through all of these messages, and as a result, it's hitting this database really, really hard. Any other people, any other clients who are using this database are now in serious trouble because the latency has suddenly spiked up. So now you can have this weird situation where just bringing up a stream processing task can affect the performance of some completely different part of the system somewhere else, can potentially bring the whole site down. This is really not what we want. We want to be able to isolate resource-wise stream processing jobs from the stuff serving the live site. We don't want to be able to create this kind of awkward situation because in normal like live traffic, you don't get these kind of spikes normally, whereas a stream processing job can produce incredible spikes. So what's the solution here? Well, I propose that in addition to that page view event we've been talking about, we add a second event type, and I'll call it profile edit event. And so we can now have a stream of events every time somebody edits their profile, which is not that frequently, but often enough. Someone, adds a new job title or changes their location or something like that. Every time someone updates their LinkedIn profile, we send a message to the stream, and we include their old LinkedIn profile and their new profile. And it'll look something like this. I've left out most of the fields, of course, but you get the idea. This person has just moved from San Francisco to New York and changed industry. Now, you have this stream of profile edit events, and because it's a stream, you can consume it with something like Samza. And now, every time you get a profile edit event, we can write it into a database. And this can be the stream processing job's own database. It doesn't have to be the shared database of profiles that's shared with everybody else. It can be its own one, so it can hammer it as hard as it wants and not affect anybody else. Now, this is quite nice, actually. If we can construct this so that this stream of profile edit events goes back to the beginning of time, just assume that that's possible for now, so that every single time anyone has ever edited their profile, we can capture that event, we can process that whole thing. Well, if you process that entire history, what you've done, and written each of these messages to your little database, what we've done is created a copy of the entire profiles database. We've basically replicated that database into our own private copy here, which is accessible only by our stream processing job. That's kind of nice now, because we've got an up-to-date database of profiles, which is not our main database, it's just our own replica, and we can talk to it in whatever way we like. So now, bring page view event back into the scene again. So remember, we're trying to enrich the stream of page view events with profile data, and that's now no problem. So when a page view event comes in for a certain profile ID, we can just talk to our database, get that profile back, and include it in the event, emit the result back out again. This is now quite nice, because now that we've got our own private copy of this database, it actually doesn't need to live on a different machine anymore. It can live on the same machine as the stream processing job, thus cutting out all of that latency. And unlike a cache, which runs into problems of invalidation and staleness, this replica database gets kept up to date straight away, whenever somebody edits their profile, the change is reflected in our local copy. But we can't just put that database here on the same machine. We can actually move it into the same process as the Samza job. And Samza actually includes an embedded key-value store, which runs in the same JVM process as Samza itself. At the moment, we're using LevelDB for that, but we're actually switching over to RocksDB because that seems to be performing better. And it's this really beautiful pattern whereby you can take in this stream of change events, build your local replica of some data, talk to it incredibly fast, much faster than you could do over a network. And most importantly, it's isolated. It's resource isolated. So if you get a throughput spike like this, you're not affecting any other application in the system. You're only hammering your own little copy of the database. So if you look at this, what have we done here? Well, actually, we've just reinvented a join. It's like 1970s relational algebra all over again, and somehow we've gone a very circuitous route and reinvented the join. And I kind of think like a lot of NoSQL databases have in recent years been talking about getting rid of joins, and you can denormalize your data and not need any more joins. And I think that's actually very short-sighted, because in the end, there's a limit to how much you can denormalize. You can't just stuff everything into every event. That would just bulk everything out incredibly and make everything slow. Joins are still necessary. I would say joins are not dead. In fact, I would kind of argue that with these systems which can perform joins efficiently, we can see a kind of return of the join back into our data systems. But aren't joins terribly slow and scale badly, you say? Well, actually, they don't have to. We can arrange things in such a way that joins scale perfectly well. I told you that they're fast because they're actually just like querying something which is in your local process. You're not even talking across the network. And we can scale them through partitioning. So each Kafka topic is actually partitioned, which means you don't have just one stream, but for one topic you have many streams, and each of these streams can be processed independently. So you can then parallelize and have each of the tasks processing its own partition of the input stream. And now if you want to join two streams together, so you have the page view event and the profile edit event streams, you just need to arrange things in such a way that the events which belong together end up together on the same task, which means that, say, for user 1234, if there's a page view event for user 1234, that goes into partition 1 of the page view event topic. If you have a profile edit event for the same user 1234, that goes into the partition 1 of the profile edit event topic. And now you take the two partitions 1 and give them to the same stream processing task. You take the two partitions 2 from the two input streams and give them to the same different stream processing task. And this way, you can co-locate the things which need to be joined together. You can parallelize arbitrarily. It scales horizontally, and it works beautifully. Anyway, so I said I was going to talk about two different applications, two different use cases. That was number one. The second one I want to talk about is data standardization. If you were at Vitaly's talk earlier, you will have heard a bit about it already. He was talking about LinkedIn's data standardization from a data science perspective. I'm going to talk about it from a data infrastructure perspective. What do I mean with standardization? So if you go to LinkedIn and you click the advanced search button, you get a form which looks something like this with lots and lots of boxes. If I zoom in a bit. What I want to point out here is that, of course, you can search for people by name or by company name or by location or by which industry they're in or any keywords that appear on the profile. But there are also a few other things you can search by. For example, here's a selection of functions that you can search by, which includes academics, accounting, administrative, business development, and so on. So these are kind of standardized job titles, you could say. So from the huge diversity of job titles that people put on their LinkedIn profiles, they've been kind of boiled down to sort of common categories. They've been clustered. They've been classified into useful kind of top-level categories. The user hasn't selected this function themselves. This has somehow been done automatically. LinkedIn calls this inferred identity, where you supply some information on your profile, but then actually some machine learning processes and data science magic goes on in the background to interpret that data further and, for example, classify it like this. There's also classification by seniority level, for example. If you're wanting to find people at the board level, for example, you can get them, and so on by company type. So let's just use as an example job titles. Software engineer is a fairly common job title, but people might also call themselves a developer. And in order to perform this kind of search, if a recruiter is looking for all software engineers, they probably also want all of the developers in the search results. Similarly, people might call themselves a computer programmer. And again, these kind of synonyms we should resolve and all kind of map to the same concept. And people put all sorts of stuff on their profiles, right? So in the end, what we want to do is interpret something. And if someone writes code magician as their job title, if we can interpret that and say that for purposes of the search results, that can be software engineer. But just to tell you that this is not quite straightforward, like a word like developer, depending on the context, could mean a different thing. Like in the real estate industry, if you're a developer, you're probably someone who doesn't write software, but someone who develops property. So I'm just saying this to make the point that this kind of standardization is actually fairly tricky stuff, and a lot of work goes into it. So how do these search indexes get updated? If you type something in this advanced search form and you're looking for someone in a particular function, you're hitting some kind of index, and every time somebody edits their profile, that change in profile has to be reflected in the index so that you appear correctly in the search results. Again, that kind of thing has to happen fairly quickly because, say, I edit my profile and I put some new keyword, buzzword on it, and then I hit the search page and try to see whether I find myself in the search results now for that edit that I've just put in. Of course, we want you to appear in the search results, so we want that index update to happen within a couple of seconds, really. So that means, again, sorry, offline batch job is not good enough. We have to do this as a stream job. So, there's this kind of blank space here in the middle. We've got this incoming stream of events every time somebody edits their profile, and as a result, we somehow want to update the search indexes using these kind of standardized job titles. And, well, I guess we need some kind of stream processing job in there. We'll call it a standardization job, which takes something like a code magician job title and outputs a modified event, which includes the original job title, because, of course, we respect what the person put on their profile, but also includes an additional field, which is their standardized job title, which in this case would be software engineer. And that's a new stream from which these indexes can then be built. Now, what actually goes into this job? Well, Vitaly talked about this already. I'm just going to treat it as a kind of magic black box for now. These are models that are trained offline. They're validated offline. People eyeball the results to see whether they're reasonable, run it against a bunch of test data sets, check some metrics, and so on. Eventually, they decide, OK, we've got here a classification model or a standardization model, which is better than what we had before. So they want to deploy this better model. Now, what happens? Well, if you deploy a better model and you start up your stream processing job with this new model, cool, that's nice. So everyone who edits their profile from that point forward, their profile edit will go through this new classification model and be updated accordingly in the search indexes. But what about all of those people who edited their profile previously? They're not just going to go and edit their profile again just to do us a favor here. So what we have to do is actually reprocess every single of the existing profiles with our new classification algorithm and update the indexes accordingly with the potentially updated better classification or standardization. And this reprocessing all of this historical data is fundamentally a kind of batch job. We have now the same logic in two different places. We've got, for our near real-time updates, whenever somebody edits their profile, we should reflect it in the indexes. That's a stream process. But now we also have this separate batch process for whenever our classification logic changes, we need to rerun over the entire data set. Now, we actually implemented something like that, and it looks something like this. So you take your stream of events. On the one hand, you send it through a stream process, On the other hand, you write them to HDFS and from time to time run big MapReduce job over the entire thing. And then you somehow have to merge these two results together so that both the real-time updates and the reprocessed historical updates end up eventually in the search indexes. You might have heard something like this referred to as a lambda architecture, which is essentially code for implement your same logic on two different frameworks, once in a batch processing framework and once in a stream processing framework. And that's certainly a way of building things, and we have built things like that. So there's nothing fundamentally wrong with it, but it doesn't seem like really the ideal way of doing things, because to be honest, it's hard enough to write your job on one framework and tune it and make it run reliably. It's even harder to do that same thing on two different frameworks. So we were thinking, why can't we do both the batch and the stream processing on essentially the same framework? And Jay Krebs has called this the Kappa architecture because everybody needs a Greek letter, which is essentially just this idea. Like, if we make a stream processing framework that's good enough and fast enough, then we can actually use that to reprocess historical data as well. And just to illustrate what that actually looks like, so this is our partition stream here. And I'm assuming here that all of the old events are on the left-hand side, new events are on the right-hand side, which means that whenever new events are added to the stream, they basically get appended on the right-hand side. And now Kafka has this nice ability, actually, to be able to maintain the complete history of these events, going back to the beginning of time. And you'll say, doesn't that take like all the storage in the world? And the answer is no, not necessarily, actually. So what you can do here is that if this stream represents something like a profile edit event, where there's a key, the key is, in this case, the ID of the profile, which was edited, then we can apply some compaction rules. That is, when somebody edits their profile several times in a row, we only need to keep the most recent edit. Assuming that edit contains the full information, all the profile information that we need, we can throw away any previous edits. We can compact those away, kind of a garbage collection process. But that allows us to make sure that even if somebody last edited their profile 8 years ago, that's still all right. We can still keep that event in the stream, and it won't get thrown away as long as they don't edit their profile again. So that lets us maintain the entire contents of, this is basically like a replicated database written in a log form. Anyone who's consuming the stream now any real-time consumer will be somewhere close to the head of this stream. So this is a stream processing job which is trying to keep up with the real-time events as they come in. So whenever somebody edits their profile, to quickly standardize their job title and update the search indexes. Now I was saying batch processing within a stream processing framework. We can do that by starting up a second stream processing job. And that second job begins at the beginning of time, offset 0 we call it, at the oldest messages that we've maintained here, and just does a linear scan through the entire thing, from the oldest, and just gradually works its way forward. And that'll take a while, but that's all right. You can just add some computing resources, parallelize the thing across multiple machines. That's all right. So from this one stream of events, you can now run two versions of the same stream processing job. The version 1 job, which is the old job, which continues processing the real-time events, and the version 2 job, which starts at the beginning of time and crunches through all of the historical data. And each of these jobs can write its output to a different location. What this means is now you have a kind of version 1 output and version 2 output. Version 1 output contains the real-time updates of anything that's happening right now. Version 2 output is being backfilled from all of the historical data. Any clients will, by default, look at the real-time output because that has the up-to-date data. But eventually, that version 2 job will catch up with the version 1 job. Once it's caught up, actually, we've reprocessed all of the historical data, and it's just acting as a real-time job from that point onwards. So now our version 2 database is up to date. The clients can just switch over, use that whenever they're ready. And this way, we've now actually implemented a very smooth transition from batch to stream within the same framework. those are the two things I wanted to talk about. That's all, really. So example one was about doing joins within streams. This is a very powerful thing, and I think we should really be thinking how we can model our applications and our systems around this idea. But in order to do joins, you need to maintain state. You need to maintain the random access state of the thing you want to join against, and you can run into resource contention problems if this is some kind of shared database. So it's really nice to be able to replicate that state, co-locate it with the stream processing job on the same machine, making it really fast and making it isolated so that when you're hammering it really hard, you're not affecting anybody else. The other thing I was talking about is this idea of reprocessing streams of historical data, thus basically doing batch processing within a stream processing framework so that you only need to write your code once against one framework, not twice. The whole thing is based on Samza, which provides high throughput stream processing, and we've really been focusing on the operability, the operations, making it really reliable and just predictable, making it really solid. So actually a lot of fancy features that we wanted to put into it we haven't done yet because we've just been focusing on making it rock solid. That's really all I wanted to talk about. There's a bunch here, you can find the slides online. Lots more to read on these various topics. Lots of people brighter than me have written about these things, so you can read their fantastic articles there. So I think we still have a few minutes for questions. You can also then find me tomorrow or later this evening. I'll be doing one of these roundtable thingy. What are they calling it? I forget. Sorry? Office hours, that's the one, exactly. Tomorrow afternoon as well, or find me anytime. But any questions, please?
I'm a little confused. When I combine those two workflows together, so in one you assume that your profiles are co-located with your processing. In other, you're changing actually profiles by changing the title. So how do you propagate those changes to the node? This change doesn't go through the processing node that you join of ID with title, right?
So I don't quite follow.
So basically, you're now, like when you're doing the join of profile from the process file, right? You're assuming that the local database, so to say, will keep the up-to-date version of the profile, right? But at the same time, you're doing, let's say, this profile edit that actually goes to another view and update is going somewhere like totally different file. Right? So how do you make sure that that change and this change are sort of stay synced?
Oh, okay. So just to repeat the question for everyone. So you've got this one stream of profile edit events. On the one side, it's going into this replicated database where you're joining it against page view events. On the other side, it's going into the standardization pipeline. So how do you coordinate those two, is the question?
Yes, because you're changing the title. Eventually, for the standardization, output of the standardization pipeline is change the title, right?
Oh, yes.
And you want to have that change title in your join table, right?
Yeah, so if you want the standardized title in the join table, then you would make this join table by consuming the standardized event rather than the original ones. So the idea is that you can compose these data flows simply by one stream process takes one input, produces another output. Like in MapReduce, one input directory on HDFS, one output directory on HDFS, and depending on which input you read, well, that's the data that you'll get. There's no, there's no coordination across the entire system that happens here. It's just a matter of who do you choose to listen to. Does that make sense?
Yeah.
Okay. Another question? Yeah, so how would I compare Samza to Spark Streaming and Storm? The short answer is look under Samza documentation. There's a detailed comparison of the various frameworks. I think there's definitely a place for all of them. They each have their advantages and disadvantages. What I've tried to illustrate here with the joins and the reprocessing are two things that are unique to Samza. So that's kind of why I highlighted them. But I suggest you look at the docs for fuller details.
You could do both of them in Storm as well. They have join operators as well as running people follow it.
Well, so in Storm, for example, there's no concept of this local state, really. So you can have a cached view onto a remote database, which has the isolation problems that I talked about. You can do in Trident a join within one microbatch, but as far as I know, not across multiple microbatches.
So in the join, you have like a database. So for shards, let's say from 1 to 4, it writes signals to one database there. And what's the reliability that if this database goes down, what happens?
So is this in the case where you've replicated the database to be co-located with the stream processing job? Yes, exactly. So the question was, what happens if you lose a node, if that goes down, what's the reliability there? That's actually a very neat feature of Samza that I didn't have time to talk about, but the idea is that every time you change any of the state in your local database, that's actually written out to a persistent change log, somewhat like a write-ahead log. But that's distributed across multiple machines. So if you lose a node, you can actually rebuild that state by reconsuming that log.
Question. You mentioned, like when you started your presentation, like, there is a profile database, which traditionally was maybe RDBMS kind of system. And there's a latency problem there, and because of that, the level DB and DB kind of solution makes sense to isolate that into every node, right? So it turns out that you're basically trying to create a replica of that RDBMS into this smaller sets of this databases.
Yep.
So how do you start building it? There has to be a starting point, right? Because how do you start? How do you start building those? I mean, is there a tool or what kind of mechanism?
Yeah.
For building that?
Yeah, so if you want, I'll just repeat for everyone. So if you want to build these kind of little co-located replicas of some database somewhere over there, how do you start? Like, how do you actually bootstrap this in the first place? So LinkedIn has a system for this called Databus, which I think one of the links here is a paper on Databus where you can see how it works. So it's somewhat like a message broker in its own right, actually. In this case, there's actually an open source version of it for Oracle, which it uses triggers to, every time you make a write, log that into a separate table, but then also has a process which keeps the history of the state of the entire database, which allows you to then jump back, consume the entire thing. So kind of doing a table scan over the entire thing, basically, but using a read-only replica so it doesn't affect the production database. And then continuing consuming the real-time updates as it happens. So that's kind of a separate piece of infrastructure. Like Facebook has a similar system called Wormhole. I believe others have written a similar thing. What we'd like to get to in Samza actually is, at least for popular open source databases like MySQL, Postgres, etc., to be able to just point your Samza job at one of these databases and say, hey, act as a follower, act as a slave of one of these, please. And it will do then exactly that. So it will have to backfill the entire history of what's there and then keep consuming the write-ahead log or use triggers or something of that sort to get real-time updates. That's not there yet, but that's in the plans.
With the proposition of backfilling and reading the whole history, are there any special considerations in your Kafka deployment to avoid thrashing with page cache-centric design?
Okay, so the question was, in our Kafka deployment, are there special considerations to do with page cache thrashing? So if we are reconsuming a whole bunch of historical data, will that interfere with the real-time consumers? Is that right? Yes, so there are some things which happen there. Number one, a really simple option is just run Kafka on SSDs. So then you don't incur that really big cost of random seeks. That in itself actually helps a lot already. We do a bit of additional things, like, for example, Samza actually runs off a dedicated Kafka cluster, so that if Samza hammers Kafka really hard, it doesn't affect other systems. Any if you want to consume a particular Kafka topic within Samza, it actually has to be mirrored from the kind of main production cluster into the Samza cluster, and then the jobs can consume it there. That's kind of an additional level of isolation, and it also means the data flow stays a bit clearer. It stays a bit clearer of who's consuming what and who's producing what and where's the data actually going. But that seems to be enough. So otherwise, it's not actually a big problem if people start consuming a lot of historical data. Right at the back, please.
With the joins, if I have 10 joins instead of 1, how can I solve the locality problem if I can't solve all of those mistakes?
Good question. So if you have 10 joins instead of just one, how do you solve the locality problem? I think the simplest answer is probably actually to make each join a separate job. That's not really a great answer, but it kind of comes down to what problem you're trying to solve with the joins. So like in a data warehouse, you would have very high dimension joins because you're joining against all of your dimension tables. In this kind of scenario, if there are lots of different keys within one event by which you want to join against things, that may have to be a series of jobs in sequence where you keep repartitioning on the appropriate key for each level of that cascade if you can't put that all together in one job. Does that make sense? Yes, please. So the question is, do you want to use Kafka as a long-term storage, keep data in Kafka forever? For keyed type data, so where, like these profile edit events that I was talking about, that does actually make sense to keep the data there forever, because the size of the data is actually proportional to the size of the data set, because you can, if the new edits come in, you can keep compacting. For stuff like tracking data, on the other hand, compaction doesn't really make sense. So you can only, there's no key which overwrites another key. In that case, what you can only do is keep a certain time window worth of data online. So I think LinkedIn's Kafka clusters keep about 2 weeks worth of tracking events accessible. So that's the time period over which you can go and reprocess things. If you want to go longer than that, you still have to go to HDFS to find the archive data. So I think for tracking type things, it probably wouldn't make sense because Kafka does scale fairly well, but not to the extent that HDFS does. It's simply not designed for that.
So when you say real time, like what's the time from when the event was created, let's say someone changed the profile, to the actually it's visible in the search?
Mm-hmm. So what's the latency through these pipelines? So our design target with this is roughly a couple of seconds at most. In practice, it's often actually lower, but so Kafka itself can achieve like sort of single-digit milliseconds if you're using the new APIs. So that's, to be honest, it's getting that super low hasn't really been a priority for us. We've mostly been focusing on the throughput rather than the latency. I wouldn't quite use this for like a high-frequency trading system yet, where you really need to shave off the microseconds. But like being well under a second is definitely design goal. A couple of milliseconds would be good. How do we address what? Sorry? How do you do high availability if we're keeping events for a very long time? Oh yes, so if a node goes down, Kafka replicates its data across multiple nodes, and if you lose a node and you have to provision a fresh node, it will actually copy that entire data set from the existing nodes before it actually joins the cluster. So that makes sure that all your data is always replicated. I think we need to cut it short, but I'll be here, so feel free to come over for questions. Thank you.